Welcome to another podcast. In this episode, we're going to be taking a look at damped vibration analysis, which is basically just an extension of what we talked about on Wednesday, except now we have damping, whereas on Wednesday, all of the problems were undamped. Just want to take a quick look at where we are this week. In terms of our announcements and things like that, we are working on material out of section 4.4 today. This is the last little bit of material that you need to finish out the Maple quiz for this week. You do have a quiz and a Maple quiz due this Friday at 11:59 p.m. And we are covering all of Chapter 4 in this week. So I know it's probably a pretty packed week. There's really a lot of information on Monday that you really need to kind of grasp hold of. If you haven't gone back and worked through several of those kinds of problems and examples in the textbook from section 4.1 and 4.2, I would recommend you do that prior to the quiz. But today we're going to be talking about damped harmonic motion. Now, the thing to remember with damped harmonic motion is we're looking at this oscillator equation. So this is called the standard oscillator form, or the oscillator form. It is a forced harmonic motion situation. So this is the forcing term. And the difference today is we have a damping term. So the equation that we looked at in class on Wednesday, where we talked about beats and true resonance, just to give you an idea, was this equation. So today, instead, we're going to look at what happens to an oscillator when you have damping involved instead. And there's going to be several variables, parameters that we're going to be using throughout this. Omega naught for us will always represent the frequency of the undamped system. It's called the natural frequency. We're going to have a different frequency here. When you have no damping, whatever omega naught is, that's the frequency of the system without damping. So that's the frequency of the homogeneous solution. But with damping, the homogeneous solution has a slightly different response. And so we're going to look at that response today. We're going to call that eta. That's the damped system's response. Omega naught is the natural or undamped response. And then omega is the driving frequency, the outside frequency that's pushing the system to respond or adapt. So what I want to do is find the general solution to this equation. We're going to find both the homogeneous solution and we're going to find a particular solution. And we will be using exponential response. So if you need to go back and review the exponential response theorem from last time, we're going to be using that just like we used it on Wednesday. So to find a general solution, I'm going to start by finding the homogeneous solution. And the homogeneous solution is going to involve the characteristic equation, which is r squared plus 2pr plus omega naught squared equal to 0. And I'll remind you, there's a really good reason for having this be 2p instead of just 2. And that is so that these characteristic roots look nice. If you use quadratic formula on this, you will get negative p plus or minus the square root of p squared minus omega naught squared as the roots. And we're going to assume throughout today's lecture that we are in the underdamped case. The reason that I'm assuming we're in the underdamped case is the purpose of today's lecture is wanting to observe the what happens with the oscillations in the response, and you don't get oscillatory behavior unless you're underdamped. So underdamped means that we have a complex conjugate pair of roots. So the best way to express that is to factor out a negative 1 here, which square root of negative 1 is I, and switch the order that these occur in. So now I'm assuming that we're in the case where omega naught squared is greater than p squared. That's what it means to be in the underdamped case, is that we have a positive radical times I here. So we have a complex conjugate pair of roots. Now, eta is the frequency response of the damped system, so that's what this value is right here. Eta is the square root of omega naught squared minus p squared. That is the damped homogeneous frequency. Okay, with that in mind, what we can then write down is our homogeneous solution is e to the minus pt. That's coming from the real part of the root. That's the exponential here. And then we would have a complex exponential, but we take its real and imaginary parts, and we get C1 cosine. It would be, if we're going to call this term eta, then it would be eta t plus C2 sine eta t. So this is what we have going on for our homogeneous solution. Now, to find the particular solution, we're going to use exponential response. So here's the idea. Our forcing function is a cosine omega t. So if you look at the original differential equation here, the right-hand side is a cosine omega t. The complex form of that is a e to the I omega t, because remember this is a cosine omega t plus I sine omega t. So you can see that a cosine omega t is the real part of this. So we know, just kind of combining the two, the real part of this complex forcing term is the function f of t. All right, so what we do is we have a complex differential equation that we're going to look at instead. So z double prime plus 2p z prime plus omega naught squared z equals, and we're going to replace the cosine term with the complex exponential term. All right, and so since I omega t, the frequency here is I omega, is not the same as these roots, right? The roots of the characteristic equation are not I omega t at all. They're I eta. Minus p plus or minus I eta are the roots here, and that is not I omega. So since we're not in a situation where the forcing term has the same roots as the homogeneous equation, we're simply in case 1 of the exponential response. So case 1 says that our solution is aei omega t divided by the characteristic polynomial evaluated at alpha, which is I omega in this case. And so the characteristic polynomial here, you could see it just above right here. For the values of r, we're going to substitute I omega into this equation. All right. So let's write all of that out real quick. So I omega squared would be negative omega squared, because I squared is negative 1, plus 2p I omega plus omega naught squared, which I would recommend that we write this way. Omega naught squared minus omega squared plus I 2p omega. So I have it written as a complex number in the bottom. This is the real part of the complex number. This is the imaginary part. So that's ZP. Now, if we were to continue going with this, what we've done in the past is we need to get the I out of the denominator so we can determine the real part of this, which is what we want to recover YP, the actual particular solution. So what you typically will do here is you will multiply by the conjugate, okay? That's one thing that we could try. There are many different ways that you can go about doing this problem. We'll just do it that way, okay? Because I don't want to confuse you, because there's a polar form of this that we could do as well. But I think it's just best to multiply by the conjugate here. So what we're going to take is multiply the top and bottom by the conjugate of what's in the denominator. So we're going to multiply top and bottom by this term. When we do that, we get a omega naught squared minus omega squared minus I 2p omega e to the I omega t. And then in the denominator, remember anytime you multiply a complex number by its conjugate, you square the real part, you square the imaginary part, and you add them together. So the bottom is going to be omega naught squared minus omega squared quantity squared plus 2p omega squared. So now we have a denominator which is real. The only imaginary term is right here. So I'm going to make this a little bit easier on us to determine the real part. I'm going to write a over all of this here. And I should just go ahead and, instead of writing e to the I omega t, write it using Euler's formula. This will be cosine omega t plus I sine omega t. All right, so now what I want to do is recover the real part. So yp is the real part of this complex solution, since cosine was the real part of the complex exponential. And all of the terms are going to have this, so I'm just going to go ahead and write this part down. And then what I want to pull out from this are the real parts. So notice if you take omega naught squared minus omega squared times cosine, that's real. So foiling these out, those would not have an I. Those would be the real part. The other real part is if you took the last terms and foiled them. So I times I is -1, which would give me plus 1, 2p omega times sine omega t. So the real part of this is going to end up being omega naught squared minus omega squared times the cosine plus 2p omega times the sine, right? And we know that since this is an oscillation of cosine and sine, both of the same frequency, we can write this in the form cosine omega t minus phi times some sort of amplitude, right? And since I'm using capital A here, I don't want to use capital A again, so I'll just use capital B, where B is the amplitude of this oscillation. Okay. So what we can quickly do then is we can say, all right, we've got, so yp is a times, it's going to be times this amplitude. And the amplitude is c1 squared plus c2 squared, the square root, right? So it's going to be the square root of omega naught squared minus omega squared squared plus 2p omega squared. Because that's your c1 squared right there plus c2 squared right there. That's the b value, that's the amplitude, all over, well, if you look at that, it's the exact same thing that occurs in the denominator, which is going to make this nice here in just 1 second. But then we end up with cosine omega t minus phi. And if you notice, since these are the exact same thing in the numerator and the denominator, this is a 1/2 power in the top, this is a power of 1 of that quantity in the bottom. So these would simplify as a square root in the denominator of that term. All right, so What we have here is we had the, let me just kind of write where we are at this point. We have y double prime plus 2py prime plus omega naught squared y equal a cosine omega t. And what we have found is that the solution to this is e to the minus pt c1 cosine eta t plus c2 sine eta t, right? Plus a times, if you look, I've got 1 over this thing. I'm going to call that a function of omega, because remember, we would know omega naught and we would know p because they are part of the oscillator. What we're looking to vary in this problem is omega, because in this example we're looking at the value of omega, which produces the largest amplitude response. And so I'm just going to call this g of omega here for just a second, and we're going to define what it is, times cosine omega t minus phi. So our work on the problem above gave us that this is the solution, and this is where eta is the square root of omega naught squared. So if you go back up here and look at eta real quick, where we calculated eta, it's square root of omega naught squared minus p squared. Okay, so what are the pieces of this solution now that we have done the work? Well, we already know what eta is. We know what p is. A is the original amplitude of the forcing term. G omega. Now, if you look at the effect that g omega has, g of omega is multiplied by a, so it's like a percentage increase or decrease of the original amplitude. In other words, if g of omega is 1, then this quantity here is called the steady state, because as time goes on, this quantity here will disappear. We've called it in the past the transient. So as t goes to infinity, because of that exponential, this term disappears, which leaves me with just this term. This is a steady state oscillation. And what we're trying to understand here is if the original oscillation had amplitude A, the forcing function had amplitude A, how does the system modulate that incoming amplitude? And this function, g omega, tells us how that incoming amplitude is modulated in the steady state. So if g of omega were 2, then the system doubled the amplitude that's coming in. And this is a function of omega because remember, as we get closer to the natural frequency of the system, what we learned on Wednesday was the resulting amplitude of the oscillations here will get bigger, right? We talked about that in Wednesday's class. So this function g of omega is very, very important. It's known as the gain. Let me write down its formula, and it's best to memorize this formula. So it's 1 over the square root of omega naught squared minus omega squared squared plus 2p omega squared. So this is the gain of the oscillator. In some ways, it tells you the percent increase or decrease of the forcing amplitude due to the system response in steady state. And it is a function, like I said, of omega. Omega naught is known, p is known, omega is the thing that's unknown here. Also, the other part of this formula that we haven't figured out is phi. We're sort of familiar with phi. This is the phase lag. If you look at where phi would come from, remember phi is the arctangent of C2 over C1. So it would be the tangent inverse of 2p omega over this term. So phi, which is also a function of omega, is defined as the tangent inverse of 2p omega over omega naught squared minus omega squared. So basically everything I have on the screen right now, you really need to commit to memory and make sure that you understand it, because you don't want to have to rederive it. I want you to just be able to use these formulas to answer the questions that are to come. Now, we haven't actually answered the question for example 2 just yet. What I would like to be able to find is a value of omega that makes the gain as large as possible, because the larger the gain is, the larger the amplitude response. And I would like to know, if I'm designing an experiment or something like that, or I'm modeling some sort of mechanical system, I'd like to know, is it possible for me to have amplitudes of oscillation that are outside of certain bounds? And what we can be able to determine is the largest possible amplitude response that we would have for any source of input. In other words, say you're designing a circuit and this is the alternating current that's coming into the circuit. You would like to know, is the circuit going to fry before you have to actually hook it up to something? And you can do that by calculating the gain. The gain tells you how much the incoming amplitude or the incoming voltage would be modulated by your circuit. What we want to do, however, is find the resonant frequency, which is the value of omega which produces the largest response. In other words, here's our goal. We want to find the value of omega, and we're going to call this value omega sub r, which maximizes the amplitude of the response. But maximizing the amplitude of the response means maximizing this function, which maximizes the gain g of omega. And then once we do that, then the largest amplitude response would be the original amplitude of the forcing term times the function g evaluated at omega r. That is the largest amplitude we would ever expect to get, is the original amplitude of the forcing function times the gain at this maximum value. So whatever the maximal gain is will occur at this resonant frequency. Now, we know exactly what this is going to be if we don't have damping. From Wednesday's class, we know that you get a maximal amplitude response in the resonant case, and the resonance case happens exactly when the driving frequency omega matches the natural frequency omega naught. So you can see here really quickly what we're going to get in that case. If omega naught equals omega and p is also 0, then this is 1 over 0. It becomes infinitely large. So you can see that without damping, if omega naught were to equal omega, this can become unbounded. But since we have a non-zero p, we have a damping term in this problem, then this thing cannot become unbounded even if the natural frequency of the system matches the driving frequency. However, it remains to be seen whether that will actually give us the maximum response. And spoiler alert, it doesn't. So I want to look at this real quick with you in Maple. So what we have here is, I'm trying to find the resonant frequency of a damped harmonic oscillator. This is the differential equation that we just analyzed together. Here is its solution as given to us by Maple. Notice the homogeneous roots, e to the minus p plus or minus. We switched it so it would be I omega naught squared minus p squared. So these are the same roots that we got. This looks like a mess until you realize that the denominator here factors into omega naught squared minus omega squared squared plus 2p omega squared. So I was just testing to see if that was indeed the case. This is kind of a valuable command if you aren't familiar with it. It's called the test equation command. You set two quantities equal to each other, and Maple will tell you if they're equal or not. So it is the fact that this is exactly what we obtained in class, obtained together in the notes just a second ago. So I'm focused on this term. I'm focused on the steady state. That's where the gain function comes from. So I isolate out the steady state here. And you can see here, if you factor out cosine omega t, you get omega naught squared minus omega squared over this denominator. Plus here you get 2p omega over the same denominator. Calculated the amplitude, and then this is that gain function 1 over the square root of that stuff that we got in class together. So I've defined the gain right here. And what we're after is maximizing this function. I want to maximize the gain function. So I didn't want to do that by hand because I would have to take a derivative with respect to omega, and that's going to get kind of messy. So this is why I'm going to let Maple do it for us. Here I've differentiated this with respect to omega. And so we're going to set it equal to 0 and solve for omega. And it turns out 0 is the minimum value. So that would minimize the gain. And this is going to be the maximum value. So we were finding critical points here. This one turns out to be a minimum. This one turns out to be, both of these turn out to be maximums, but we're not considering the negative frequency. So our resonant frequency turns out to be this value, the square root of omega naught squared minus 2p squared. So it was nice to be able to use Maple to find that, so we didn't have to do all the differentiation ourselves. All right, so back to our work. We find that the resonant frequency is omega naught squared minus 2p squared. So you can see without damping, if p were 0 here, so if p is 0, no damping, then omega r is just omega naught. In other words, the driving frequency that gives the resonant response is the natural frequency. But since we have damping, notice what this does is it moves it to the left of omega naught. This value will be slightly smaller than omega naught, which is what we're going to observe here in the examples that we're about to do. All right, I know that was a lot to take in, and I know you're probably going to need to go back and work through some of this to kind of make sure that you understand it. At a minimum, you need to understand what's in this page right now. And that is the solution to this differential equation with a cosine omega t on the right-hand side is given to us by this, where this is the transient or homogeneous response, and this is the steady state response. The function g of omega is called the gain. Here's the formula for the gain. The gain is maximized at this frequency, so this function is biggest when omega equals omega r. And the phase lag is given to us by this angle phi. Knowing all the terminology, everything that I have here, this is very much worth memorizing. I will say one added caveat to that, and that is your book uses a slightly different form because they don't look at the y double prime plus 2p y prime plus omega naught squared y form. I don't know why they don't look at that because their eta is far uglier than ours because they don't have the 2p term in there. But their formulas that they derive in the textbook are based off of y double prime plus py prime plus qy. I don't mind if you use their formulas. You just cannot intertwine the two because their p is different than our p. So make sure that when you see the p in their formula, you understand it's not the same p that we have here. Their p is twice what our p is, okay? So just make sure that you understand that the book has a different formula, but if you want the formulas I recommend you use, they're these. So these are the resonant frequency gain formulas for damped harmonic motion. All right, let's see how we're going to use this. And really this is heavily formula-based at this point, the examples that we're going to look at from here on out. So memorization of that previous page is really the thing that you need to be focused on right now and understanding where those things come from. So if you look at this question here, it says, suppose that we have an LRC circuit. So here's our LRC circuit equation. We've got a right-hand side that is some incoming voltage amount A, but it oscillates or alternates, so it's an alternating current. Assuming the underdamped case, what frequency of oscillation here yields a maximal amplitude response? Well, we know that that is the resonant frequency, and we had the formula for the resonant frequency just above. So If you want to pause the video and try this out and see if you're doing it correctly, go for it. Make a choice and then resume the video and see if you are correct. All right, if you haven't paused the video yet, I would recommend you do that. Here's where we are. Essentially, this comes down to, like I said, working with formulas. So this is the differential equation that we use to derive our formulas. That's very important. And the formula that we obtained for the resonant frequency was the square root of omega naught squared minus 2p squared. Now, if you compare this with this problem, then we are looking at Li double prime plus Ri, Li prime plus Ri. So we're going to have to convert this to charge, right? So we're going to have to, the maximal amplitude response and the charge on the capacitor. So remember that the derivative of charge, moving charge, is current. So when I look at this differential equation, this is Li prime, but I prime is Q double prime, plus R I is Q prime, plus 1 over CQ equals A cosine omega t. So this is the differential equation that calculates the charge on the capacitor, and we want to know the value of omega that will maximize that charge. Now, here's the thing. This equation doesn't look like this one. Notice we don't have a leading coefficient here, but here the leading coefficient is L. So I have to divide through by L and obtain the equation Q double prime plus R over L Q prime plus 1 over L C Q equal A over L cosine omega t. So this is the differential equation that we're looking at for the purposes of comparing it here. Because L is a constant, I can just absorb it into this, so it's still just a constant times. That's not going to affect any of our formulas. But I do need to make sure that I'm picking out the correct P value and the correct omega naught value for here, okay? So our resonant frequency here would be the square root of, okay, let's start with omega naught squared. Omega naught squared would be the value in front of this term. It's just 1 over LC. So 1 over LC minus 2 times P squared. Now you got to be really careful here. P is half of the number that's in front of here, right? So if you've got a 6 in front of here, P would be 3. So half of the number here is the P value. So this is half of the number here is the P value squared. So P on this problem is R over 2L, and omega naught is the square root of 1 over LC. Okay, if you finish out the calculation here, you will get a R squared over 4. 2, 4 gives a 2. So you get an R squared over 2L squared in the bottom there, which gives answer choice B. So the frequency with which the incoming voltage is alternating, that frequency, if it hits this value, will give the largest response in terms of charge, the largest maximal charge on the capacitor for this particular circuit. All right, so here I'm going to, this is kind of similar to one of the problems that you have on your Maple quiz, so we're just going to go through this together. I'm going to do most of this in Maple with you, but I do want to just use the formulas here at the outset to make sure we understand what things you should be putting into Maple. So let's just write out the general solution since we know how to do this. Y double prime plus Y prime plus 49y equal A cosine omega t. And based on the work that we've done earlier today, we know that y of t is equal to e to the minus, well, let's make sure we understand what p is. P is 1/2, right? Because it's half of the term there. and this is omega naught squared, so omega naught is 7. So you get e to the minus pt c1 cosine, remember it's eta. Eta is the square root of omega naught squared minus p squared. So in this problem, it would be the square root of 49 minus 1/4, which is, oh goodness, 160, 36, 196 minus 1, 195. Square root of 195 over 2, I believe. There's probably a term that I can pull out of that, but we're just getting a common denominator here. So that's your eta value. So there's your transient solution. Plus, now we're going to talk about the steady state. The steady state is A times the gain times cosine omega t minus phi. Let's just quickly write down the gain function. It's 1 over the square root of omega naught squared. Omega naught is 7. Omega naught squared is 49. So it'd be 49 minus omega squared quantity squared plus 2p omega. So 2p is 1 omega squared. So this is our gain function, and our phase lag would be the tangent inverse of, basically it's this number divided by this number. So what's inside the squares here. So it would be omega over 49 minus omega squared. So we know exactly what the solution looks like. We've got the formula for this, the formula for this, and what you're going to see in Maple is as we adjust the value of omega, we get a different amplitude response out of our steady state. So let's take a look at it in Maple real quick. So here I've done the differential equation, and we did have the value of eta right. It is square root of 195 over 2. Here is that formula for the gain. And this is what the problem asked you to do, is plot the gain versus omega. So if you're looking at this plot, and this is a major plot for not only your understanding for the exam 3 that'll come up last week of class, but for this Maple quiz this week, you need to know what you're looking at on these kinds of plots. Across the horizontal axis is the frequency of the driving term. So it's the frequency at which we're pushing the swing set, or the frequency at which we're applying voltage to the system, or the frequency at which we're driving a spring in a spring mass system, right? It's the outside frequency. Remember on this problem, the natural frequency is the square root of 49, which would be 7. So omega naught is 7. We would expect to see a spike near 7. But we do know that because there is damping here, and it is light, we have light damping here, our damping coefficient is 1. We do know that the resonant frequency, in other words, where this peak is on this graph, should move just to the left of 7. So I expect to find here in a second that the resonant frequency is just to the left of 7, and that's where this calculation comes in. I'm taking, this is the resonant frequency formula here, the square root of 49 minus 2p squared, minus 2p squared. I'm evaluating that, and I'm getting 6.96. So I moved just to the left. The less damping you have, the further to the more damping you have, excuse me, the further to the left this moves, and the less damping you have, the closer it gets to 7. If I then take my gain function and evaluate it at this resonant frequency, this is the largest gain possible. So for this system, this is the largest gain, which means, now remember how to interpret this number. This number is a percentage increase or decrease of the original amplitude. So what this is telling me is my system with damping will take any incoming amplitude vibration, and it will reduce it to only 14% of it will reduce it by almost 86%. So what remains is 14% of the total value, right? So that's telling me that if I had a curve coming in that had 120 volts, it's a very common voltage number, alternating current, 120 volts, this system, if it's describing a circuit, this system would modulate that incoming amplitude to only 14% of its original value. So what you have to decide is, okay, for the circuit I'm designing, is 14% of that original 120 volts, is that sustainable in my circuit design? That's what the gain function would tell you here, is how much you can expect that outside amplitude to be modulated by the system. So we have our value. What I did was took that original differential equation I had. Once I found omega, I set omega equal to it, and I did desolve all over again. And you can see here's the graph. And it's exactly what we would expect. I looked at initial conditions at rest. So initially the oscillator is stopped, but because there is an outside force, the outside force kicks it into action, and over time it kicks it into action such that the steady state amplitude of the oscillation is, well, it looks like it's about 0.15, but we know it's exactly 0.143. If I had a bigger, I could go up to desolve and change the value of A and show what I mean by it modulating here. So if I set A equal to, say, 10, right? So that means the incoming oscillations have amplitude 10, okay? So it's sort of equated with the energy of the signal that's coming into the system, but it's not quite the same. So we've got an amplitude of 10 that's coming in. We know that the gain is going to modulate it, retaining only 14%. So we would expect, when I plot this here in just a second, that this wouldn't be at 0.14 anymore. This would be at 1.4. So let's see if we're correct. And it looks like we're good. We're at 1.4. You know, if A were 50, right? So you have to ask yourself, what is 0.14 of 50? 14 times 5 is about 7. So 14% of 50, I would expect my amplitude here to be about 7. And you can see it's right there. It's right around 7. So the gain actually tells me a lot about what the system's going to do with an input. And it's really important that you understand what the gain is telling you about the system response. All right, I just got one more little wrap-up question here. We had questions like this on the beats and resonance part. Here we have an oscillator, and it settles into a steady state. So we have some sort of damping here. You started out with a Wilder oscillation, but then it damps and settles into a steady state. Which of these differential equations below could have produced this graph? So I'll give you a second to think about it and determine which one is your answer, and then we will go from there. All right, if you haven't paused the video, please do so. Let us talk about it for just a second. I know that this kind of behavior can only happen if there's damping, which means I can automatically ignore C. So it comes down to A, B, or D. And what you see is the only difference between A, B, and D is the frequency of the forcing turn. So if you go back and look at our solutions that we've obtained previously, so our answer here, this is the steady state part of the problem. So once it goes into a steady state oscillation, it will oscillate with frequency omega, which is the same as the driving frequency. So you expect to see whatever the driving frequency is in our differential equations down there, you expect to see the same frequency in steady state. So let's look at this, and I'll look here, I'll pick on 6 pi. So if we look here at 6 pi, we're at this value here. We complete one full cycle, right? So frequency is angular frequency, which these are all angular frequencies. Angular frequency tells you how many cycles you complete in 2 pi time. So 2 pi time would be going from 6 pi to 8 pi. So let me draw the arrow down for 8 pi. And if you look over the course from 6 pi to 8 pi, how many oscillations do we complete? Well, you complete 1 and 2. So since there are 2 oscillations completed in 2 pi time, I expect that my omega is 2 for this problem. And this is the only one that has an omega equal to 2. So the correct answer here is B. Now, I could have also calculated the gain to see which of these oscillators would give me a gain of, let's see, what would the gain have to be? This is a really good question. Our incoming amplitudes are 4, but our steady state only has an amplitude of 1/2. So 4 times the gain is giving me 1/2. What does the gain have to be? So you can immediately see that that would mean the gain is 1/8 or 0.125. So you could also calculate the gain function for the different values of omega that are here and see which of them gives you a gain of 0.5, but this is just by far the easier way to do it. So it's the talk today is a little bit on the shorter side. Really important idea here. The ideas on this page, they are worth memorizing. As you're finishing out your Maple quiz, you've got problem 3 and 4 that are directly from this material. I'm going to try to put this up a little bit early. This is going to go up on Thursday. That way you can look at it a little bit earlier and get to it. And any questions you have, just email me about your Maple quizzes. And don't forget your actual quiz that's due on Friday. All right, y'all have a good one. I will talk to you soon. Goodbye.